Welcome everyone. In this video, I want to look at another redox titration, and this one is quite a lot of reading, but we'll break it down piece by piece. So it says a 0.37 gram sample of molybdenum ore was crushed and dissolved in acid, resulting in a solution of molybdenate ions, so MoO42 minus, and this was subsequently converted to MO3 plus, so by a reduction process. So what you need to gather from that is MoO42 minus, and then some stuff happened, and then we got MO3 plus. Right. Then it says a 25 milliliter sample of this MO3 plus solution was titrated against a potassium permanganate solution. The average titer was measured to be 20.85 milliliter. The products of the titration are solution of manganese 2 plus ions and molybdenum O2 2 plus ions. Assume 100% conversion in all steps. Right. For this titration, answer the following questions. But before we start there, let's look at what is actually happening. So the first part is kind of, I wouldn't say an irrelevant point, but it basically just says there's a sample of molybdenum ore. So let's put that in a beaker, and there's a specific mass of it. So mass of the ore equals to 0.370 gram. Right. Was crushed and dissolved in acid. So we're not told the acids. In other words, it doesn't mean it's going to have any effect, but we just can follow where everything goes. So it means there was some acid added. And this resulted in a solution of whatever ions. So this resulted in a situation where when all the ore was dissolved, we left over with molybdenum O4 2 minus and ions. Then by some sort of reduction process, so we're not told what that process is, we're just told that there is some reduction process that occurs. Those ions are then reduced to molybdenum 3 plus. So in other words, we end up with a solution that has molybdenum 3 plus ions in it. It says then 25 milliliter of that solution, and that's the important part that you need to take. So 25 milliliter of this solution is then taken. So an aliquot of 25 milliliter of the solution is taken and titrated. So now we put that in a different beaker. So we can even, let's make it a different color so then we can remember it's a different beaker. So it's a different beaker, and there's 25 milliliter of it taken, of the molybdenum 3 plus, importantly, that is there. So, and this volume is the 25 milliliter. Right, of the molybdenum solution sample that is titrated. And it says we add to this potassium permanganate. So we can say that there's a titration that happens here. So titration, and this titration happens against potassium permanganate, which is then 0.0955 molar, and the volume of the titrate, so meaning the volume of the solution that is added on average, is 20.85 milliliter, or of course 20.85 times 10 to the power minus 3 liter. Okay. And what happens in this beaker is then, of course, some reduction process, or some what do you call it, redox reaction. So the products of this titration are a solution of manganese. So you want to put it, what happens in here, if you zoom in, is that we have molybdenum 3 plus reacting with potassium permanganate, so MnO4 minus, because remember the potassium is just going to be a spectator ion, forming Mn2 plus ions plus MoO2 2 plus. Okay, so that's what's happening in that beaker. That's how this whole thing reads. That's what you need to read. Okay, now we know that. What's the questions? The first question is, write a fully balanced ionic equation for the redox reaction taking place during the titration. So we have figured out what's the thing happening during the titration. So we can start there. The unbalanced equation is something that I've already started writing here. So MnO4 minus, so of course in the aqueous phase, plus molybdenum 3 plus aqueous, which then produces manganese 2 plus, also in the aqueous phase, plus the MoO2 2 plus aqueous. In case you missed it, where I got these products from, it's what they say. They say it forms manganese 2 plus ions and MoO2 2 plus. So that's all that I've written there thus far. It's not something that I've made up. Okay, so now we need to figure out what's undergoing reduction and what's undergoing oxidation. So if we look at the two main species, so we have manganese and we have molybdenum. Manganese is going from +7, so of course it has to be in the +7 state here to balance the oxygen, which is in the -2 state. So -2 times 4 is -8, +7 gives -1. And manganese here goes to +2. So that one is easy enough. It goes to +2. That's what happens to it. Molybdenum goes from the +3 state all the way to, okay, so oxygen is always -2. So there's two of them, so it's -4, end up with +2, so it means molybdenum needs to be here in the plus, it's -4 ends up with +2, so +6 state. So it goes from the +3 state to the +6 state. Okay, so manganese experiences a decrease in oxidation number, therefore it means it must be reduced. You can also see it because it loses oxygens. It goes from MnO4 to just Mn. It must be hence reduced. And molybdenum is then oxidized. You can see it loses electrons. It has an increase in its oxidative number. So it's oxidized. So you can go ahead and write your half reactions, your reduction and oxidation half reactions. So I'll just get you started. So your oxidation half reaction and your reduction half reaction. Oxidation half reaction is the thing that contains molybdenum. So you say molybdenum 3 plus aqueous goes to molybdenum O2 2 plus aqueous, right? And the reduction half reaction is the manganese, so MnO4 minus aqueous goes to manganese 2 plus aqueous. Okay, and then you need to go ahead and balance this. That is, I mean, honestly, you can go and do that. And you have the information because there's a separate video on how to do it in acidic media. So you know it is in acidic media because the molybdenum we added, that's the only point what the acid is important for here. We added acid at the way beginning, so it implies that there is acid here. So you can use H+. So the things that you use is H+, water, and electrons. Balance your mass, balance your charge. Eventually, you should get to a point, if you've done it correctly, you'll see you'll multiply something by 3. You should end up with 3 MnO4 minus aqueous plus 5 MO3 plus aqueous plus 4 H plus aqueous gives 3 Mn2 plus aqueous plus 5 MoO2 2 plus aqueous plus 2H2O liquid. Okay, that's the fully balanced reaction equation. So you will see there's some interesting numbers here and how you can get to them. So it is quite challenging, but you should be able to do it. And remember, it's an acidic media, so that's all you actually need. From there, it's okay. All right, so that's balancing the reaction. Determine the concentration of the original MoO42 minus. So now we're talking about this original concentration here. Now, that is an interesting question, because what can we relate to the MO4 minus? The only thing that we can relate is the MO3 plus, right? Because we know the only source of molybdenum is the M. So MO3 plus can only come from MO042 minus. So if we can get the number of mole of MO3 plus, then we know how many moles there were in the 25 milliliter sample, and then we can know what that concentration had to be of the MO042 minus. Right, so that's the logic that I'm going with, for this at least. For life, I use different logic. So let's remind ourselves of some things that we know. For the so we're going to use the titration information. We know that potassium permanganate, we were given a concentration of 0.0955 molar. We were given a volume of the potassium permanganate of 2020. Why doesn't it want to write there? 0.8585 milliliter, which is of course 20.85 times 10 to the minus 3 liter. So let's just calculate how many moles. So what I'm working towards is, if I know how many moles of permanganate reacts or was added in the titration, then I know how many moles of MO3 plus, because that's what the titration is. Remember, acid-base titration is a thing where you have your base, for example, in the biret. In this case, what is on our biret? Potassium permanganate. In other words, it's the permanganate thing, and it is reacting with the molybdenum thing. And in this case, our balanced reaction equation just says 3 permanganates reacts with 5 molybdenums. So that is what it is. We've gotten to that point now. So now we want to know, we know how many moles of potassium permanganate there is. Potassium permanganate gives 1 mole of permanganate anion for every mole of potassium permanganate. So we can go ahead, O4 C K MnO4. That's a direct relationship. You should get 1.991 times 10 power minus 3 mole MnO4 minus. Right, so that gives us the number of moles of permanganate, and now we can relate that to the number of moles of molybdenum. So we know number of moles of molybdenum 3 plus is equal to, we form 5 mole of molybdenum 3 plus reacts with 3 mole of permanganate, and that's going to be multiplied by 1.99 times 10 to the minus 3 mole permanganate. All right, so you can use your cross multiplication to get to this point, or you can just write it down, and you should get 3.318 multiplied by 10 to the minus 3 mole molybdenum. Okay, so now you have that. Now that you have the number of moles of molybdenum, what is the information about molybdenum? Well, that is the amount of molybdenum in 25 milliliter. So hence we can get the concentration. But the number of moles of molybdenum, well, MO3 plus, must be purely equal to the number of moles of molybdenum tetroxide. So in other words, we can say that this is true, as well as that the volume of this solution is 25 moles. Right, because whatever this was, this number of moles will be the same, and hence the concentrations will remain the same throughout, because they're 1 to 1 to 1. It's another special case where we can do that extension of logic. So it means the concentration of MO042 minus is equal to the number of moles of MO3 plus divided by the volume of the solution, and that's going to be equal to the 3.31 times 10 to the minus 3 mole divided by 25.00 multiplied by 10 to the negative 3 liter, and you should get 0.133 molar. Okay, that is it. Question C. Determine the mass percentage of molybdenum in the ore sample. So what do we know, right? So the question is, what are we asked? We're asked the mass percentage of molybdenum. But we've already determined what the number of moles are of molybdenum 3 plus, right? We know how much molybdenum there is, or there were, right? In other words, it means that if we were to take the sample, it doesn't matter. The only source where molybdenum can come from will go to this molybdenum 3 plus. Hence, the mass of molybdenum 3 plus in the sample must be equal to the mass of the number of moles of molybdenum 3 plus divided, of course, just by the molar mass. That's a very funky M. And the molar mass is 95.94. You should get a value of 0.318 gram molybdenum 3 plus. Okay, and that means that is how much molybdenum there is present And of course, that is meaning that is how much that could have come from the sample in the first case. So therefore, the mass percentage molybdenum is equal to the mass of molybdenum. And remember, whether or not you take mass of molybdenum or mass of molybdenum 3 plus, the 3 plus is not going to affect it because it's 3 electrons. It doesn't make that issue. The mass of the sample, mass of ore, and you multiply that by 100%. You'll get 86%. Right. So that's the basic point. It's to try and see whether or not you're able to follow where's the only source of molybdenum, and basically just can you balance a redox equation, and once you have a balanced redox equation, can you do your normal stoichiometry? So it's actually a pretty straightforward question. It seems a bit dodgy or difficult, but I promise you go through it a few times. It's not that challenging. But anyway, thank you for watching as always, and I'll see you in another video.